Hello everyone, this is chapter 22 from your textbook and the topic is electric fields. So we are going to cover the following sections. Basically, we're going to talk about electric charge, conservation of electric charge. We're going to introduce Coulomb's law, electric field lines, definition of electric field, and then at the end we're going to introduce motion of charge inside electric fields. This is just a reminder that this PowerPoint or the lecture notes only cover summary. It's important for you to go through these topics from the textbook. I'm not sure if the textbook now available on Blackboard, but it's going to be ready within a few days. Okay. So as a motivation for knowing something about electricity and magnetism, if we just look around, our technology in the last 200 years basically just depends on electricity. This video recording, for example, without electricity could not happen, right? So it's important for us to have some knowledge, basic knowledge about electricity and magnetism. And we will see that these two topics, electricity and magnetism, previously were thought to be independent from each other, but now we know that these two topics are very combined. So the idea of electricity and magnetism goes way back to Chinese, long time ago, and then Greeks. But in the recent history, the most credit goes to Europeans, scientists from Europe. For example, one big contribution was introduced by Coulomb in 1785, I think 100 years after Newton, that introduced the force between two masses. For example, Newton introduced the force, attraction force between two masses, any two masses in the universe, and this attraction force, the result of his equation is simply that this force is proportional or inversely proportional to the square distance between these two masses. Now we see that Coulomb, 100 years after Newton, comes and introduce, experimentally actually, prove that there is a force between two charges, two electric charges. So let's say two positive charge, or two negative charge, or positive and negatives. For example, these two cases, here the force will be attraction or repulsion force. Here, let's change it to positive and negative. The force will be attraction force. So in these two configurations, the force simply proportional or inversely proportional to the distance, square distance between the two charges. So it looks like these two forces in nature kind of similar. Okay, but of course we will see later on that these two forces, magnitude-wise, they have very, very different. In fact, gravitational force, this is gravitational force, this electric force, way smaller than the electric force. And then again, another 100 years later, Maxwell, the famous scientist, was able to combine electricity and magnetism into four simple equations that you can write those four equations in half page. Then many other scientists, including Hertz, for example, was able to do experimental and application on and produce actually electromagnetic waves. And we are using this application in every time we warm up our food using microwaves in our kitchens. And some of those scientists we will see throughout the chapter 22 or later on that have been credited by having their names combined to units. For example, Coulomb, we know it's a unit of a charge. Hertz is a unit of frequency. Okay. So something it's important to have information about is, we say, conservation of electric charge. So if you take any material in universe, for example, take a piece of glass or a piece of fabric or plastic or any other piece of material, simply consists of atoms. And atoms consist of nuclei or nucleus. Inside the nuclei of atoms, we have protons and we have neutrons. So protons simply elementary particles with positive charge, neutron elementary particles neutral, means doesn't have any charge. In a classical picture, we know that electrons are going around the nuclei, so electrons, and these electrons also are elementary particles having charge of negative charge. So in any material you take, the number of electrons simply is equal to the number of protons. Number of electrons is equal to the number of protons. Means number of negative charge is equal to the number of positive charge. That's why materials by default are neutral. Okay, total charge simply is constant. But for example, what happens is when we have a piece of glass and we rub it against a fabric. So in this case, we will see that some electrons are going to move from the glass to the fabric. So in this case, the glass will end up with having less number of electrons. So the glass will end up to be a positive charge. And of course, the fabric will get more electrons, so it's going to be a negative charge. Okay. So it looks like in this process, nothing was created. It's simply something is moving from one material to the other material. But the total number of electrons in these two materials, total number is simply constant. Okay. So it looks like this process is quantized. So the charge is quantized, means either one electron is moving, two electron is moving, 3 electron is moving. Okay. You don't have 2.5 electrons. So for that, we say the charge that the glass will end up with is simply an integer number of the number of electrons that lost or moves away from the glass. And n is simply an integer. So E here refers to the magnitude of charge carried by electron or magnitude of charge carried by a proton. So the magnitude, we put this two vertical line, this is the magnitude of the charge, is equal to 1.6 10 to the power minus 19 Coulomb. So for electron, the charge of electron is a negative of this value, and the charge of proton is the positive of this value. Okay, so it's important. Conservation of charge, number of charge, simply the total number of charge is constant. Now, if you bring these two charges, for example, maybe I forgot something. Let me go back to this slide. So if you replace the glass to a piece of plastic rod, so instead of this glass, we have a plastic rod and we rub it against the fabric. In this case, again, there would be a transferring of electron from one material to the other material. But in the case of plastic fabric, the electron actually will move from the fabric to the plastic. So the plastic rod will have more number of electrons, so it will be negative, right? So if you do this experiment twice, once with a rod, one with a plastic, you will end up having a positive glass rod and a negative plastic rod. So now what happens if you do experiments with this rubber or plastic and glass rod? So what will happen is, for example, here, if you have a positive glass rod and a negative glass rod, and you try to get them close to each other, you will notice that actually they attract each other. If you repeat the same experiment, this time with two rubber rods, and because each one is negative, they actually repel each other. And Coulomb was the first scientist that experimentally proved that, showed that, and quantified using some parameters, and the equation simply called Coulomb's law. Okay. Now, based on this based on the phenomena of electric charge, we could categorize all the materials into 3 categories. So the first one is conductor. So we have materials. By default, they are conductors. And we have insulators. And we have something in between. We simply call it semiconductors. So how these materials are different from each other. So in conductor, for example, think about a piece of gold or copper or aluminum, conductors by default, they have free electrons. Free electrons, not very attached, not very bound to their nuclei. Remember, we talked about atom. We said this is the nuclei or a nucleus. We have a proton and neutron, and we have electrons that classically we could say, in using classical physics, we could say electrons simply moving around the nuclei of their atoms. And basically in conductors you have one electron, or maybe two, one electron. They are not, this electron is not very attached to the nucleus. So that electron is willing to participate, is willing to actually move, simply leave the atom and contribute if electric field was applied to the conductor, so it will create a current. Example, we have too many examples like copper. That's why copper is used to make wires, aluminum, silver, gold, and most of the precious metals, falls under the category of conductors. But if you take another extreme case for insulators, a piece of rubber or dry wood or glass, they are insulators because most of or all the electrons are very bound to the nuclei. So even if you have a piece of glass or piece of wood, even if you attach to a battery, for example, we're going to talk about this later on, okay? The battery is not able to move electrons from one position to the next position because electrons are all bound tied to the nuclei. On the other hand, we have semiconductors. These are materials, in addition to electrons, it has other charge carriers called holes. So we have holes and electrons. In this course, we are not going to, going down and talk about deep down introducing semiconductors, but I'm sure there are other courses that introduce semiconductors, diodes, transistors, and other components. Okay. Now the question is it how we could charge a conductor, for example? So one method to charge materials is simply this method, by conduction, mean by contacting two materials against each other. So here, glass rubbing against the fabric or rubber rubbing against the fabric. But there is another method to charge a conductor without having any contact with another charged material. Okay. So this is called charge by induction. So it's a simple definition. What's charge by induction? It simply is the ability to charge a neutral conductor. A neutral conductor, piece of gold, piece of copper, for example, neutral. It's not charged yet. It's possible to charge this by using another charged object without having a contact between these two objects. So let's demonstrate this, at least with some images. So for example, here we have a neutral spherical shape. Think about like a spherical shape copper. So if you count the number of positive charge here, 1, 2, 3, 4, 5, 6, 7, or 8, and if you count the number of negative charge, 7 is equal to 7. So the total charge is equal to 0. Here, Q is the symbol we're going to use for charge. So total Q here is equal to 0. What happened now? If you place this neutral charge object close by, if you place it in a close proximity to a charged object. So here, let's say we have a rubber rod with a negative charge. So when you do that, because of the force between objects, between charged particles, what happens is electrons inside the neutral objects will try to move away from this negative charge. So it will move away to the right side. Now we could do a trick. We could have a wire and attach to the ground. This symbol means this is a ground. And because ground is a very big object, electron, simply the little bit excess or extra electron from the sphere is able or are able to go through the ground. So what happened now, if you cut this wire, you already know that some electrons moved from the sphere to the ground. So if you cut the wire, what you end up having is you have now less number of electrons. Okay, so next step is, if you remove this completely, you just remove it. So you end up by having a charge redistribute, of course, redistribute across the sphere. And now you have a charged object which is positive because it has less number of negative compared to number of positives. So now you have a positive charge. Okay. The question is it possible to do this process for this insulator? Somehow, yes. For example, here, if you take a it will be some charge rearrangement. Okay, you will have some rearrangement, some redistribution of the charge of insulator. So, for example, here our insulator is simply a wall. And we know a wall has painting material, so it simply consists of atoms that has electrons and protons. So what happens if you bring a charged balloon that has a positive charge? It's a charged balloon, and you placed next to the wall. So in this case, because the electrons in the wall is an insulator, electrons are bound, are tied to their nuclei, they cannot leave the wall, right? But what will happen, it will be some redistribution of charge. So electrons will try their best to get closer to the positive charge of the balloon. So you have this kind of like watermelon shape. One side will be negative, one side will be positive. Actually, this are called polar material. Polar material. So now the question is, what happens if you remove the balloon? If you remove the balloon, all this charge will go back, will redistribute along the wall, and the wall will not have any charge left. Okay, there is no positive charge, there is no negative charge. Of course, the total charge simply will be unchanged. But in this case, the total charge has changed because many electrons simply move from the spherical shape neutral charge initially, neutral object to the ground. Okay, some definitions. If you remember in physics 121, we defined point mass. Point mass in physics 121 was simply an object. Assume that all the mass accumulated at one point. This is kind of similar. We have point charge. Here we assume that all the charge on a specific object accumulated at one point. So for example, when we discuss electrons or protons, we discuss them during this course as points. They are points and simply they have Q's, they have charges. Okay. So for the electron, we have this charge and we have the mass of the, Okay, so next will be Coulomb's law. Coulomb's law. So Coulomb was the scientist who lived between 1736 to 1806 and experimentally demonstrated the existence of forces between charges. So, for example, let's take two charges, positive Q1 and again another positive charge, let's call it Q2. So these two charges, each one apply a force on the other one. So this is the force affecting on Q2 by 1. This is the force affecting on Q1 by Q2. And let's assume the distance between these two charges R. So Coulomb demonstrated that the force, the magnitude of the force F, is actually proportional to the magnitude of Q1 multiplied by the magnitude of Q2. Simply, this tells us that if the multiplication between Q1 and Q2 get larger, the force will be larger. So if the two charges are large in quantities, the force will be larger, and opposite is true. And also he demonstrated that this force, the magnitude of the force, also inversely proportional to the square of the distance between the two charges, r second, or r square, I should say. Okay. One more thing. The direction of the force is simply along the line, along the distance between the two charges. So this force is going into this direction, and this force is going into that direction. Right? Now, we could make this proportionality an equation. So F is equal to constant K, Q1, Q2, divided by R squared. Because force is a vector, so we could put a vector sign here, but in the right-hand side, we should actually define or explain that this is a vector. So we need a unit vector here. This unit vector, simply we could call it r hat. R hat. So let me write it again somewhere here. F is equal to K, Q1, Q2 magnitudes, R squared and R hat. Now R hat is a unit vector. Could be, for example, R hat could be I, could be J, unit vector J, and unit vector K. We have done this in the previous course. Or could be any unit vector in any direction. And also the force could be an attractive force if the two charges are opposite in their sign. So this is positive and this is negative. The force will be simply attractive. Okay. Now let's a little bit talk about this constant. This constant, the value of the constant is simply, it's very close actually to 9, 10 to the power of 9. So when I solve a problem, instead of this 8.9875, I'm going to just simply write it as 9. I'm going to approximate it as 9, 10 to the power of 9. And the unit is obvious, it's Newton meter squared divided by Coulomb squared. But the K as a constant is related to another constant. So K is actually equal to 1 divided by 4 pi epsilon naught. 4 pi epsilon naught. Now epsilon naught is, it's called permittivity of free space, and it has the following value. You should never memorize these values. So what's the meaning of this permittivity of free space? It simply tells us it's a measure of how much the free space allows us to accumulate charge inside it. For example, in space, in free space, if you have a positive charge with quantity Q, positive Q, and another negative charge with quantity minus Q, and let's keep increasing this charge. So let's make this one higher and higher. Let's make this one higher and higher. Well, the space does not allow you, or it only allows you to a certain level to increase the value of plus Q, minus Q, but because eventually what's going to happen, this charge will happen. So simply, electron simply will move from one charge to the next one. And this is called discharge. Okay, because the free space, the space has a limit to how much we could accumulate charge inside it. And of course, material also has this kind of limit, but in this course, we're only going to talk about free space. Okay, so the way we write Newton's second law in a vector format or in a vector form is a force equal to constant K, Q1, Q2 divided by R squared, and the unit vector here. As we mentioned, unit vector could be I, J, K, and it's important to know this is simply the distance, square of the distance between the two charges. This square of the distance between the two charges. Okay. Now the magnitude of this force is exactly equal to the magnitude of this, right? The only difference is the direction. The same true for this. Let me just remind you of the notation. So when we say F21, this simply tells us that this force is produced by charge Q but applied on charge 1. It's just a notation. Sometimes when I solve a problem, I'm going to just simply call it f prime or f1, f2, but we are just following the notation of our textbook, which is nice. Okay. Let's maybe go over one example. Now, the unit, something maybe we haven't mentioned, the unit of charge, it's simply Coulomb. Coulomb is a big unit. So we do have micro Coulomb, which is 10 to the power minus 6. We actually have a nano Coulomb, which is 10 to the power minus 9, and so on. Okay. So in order to apply this equation, we got to be careful. We need to use a Coulomb. We need to, convert the micro Coulomb or nano Coulomb into Coulomb, and distances has to be in meter, right? Okay. So an example. This example simply demonstrates the difference between electric force and gravitational force. So here we have an electron, and the electron and proton of a hydrogen atom are separated on average by a small distance, which is that distance. So think about, this is proton, and there is electron. That classical physics simply tells us that this electron is going around it. So this is proton, this is electron, and there is a distance between them. So the questions simply tell us, find the magnitude of the electric force and the gravitational force between these two, and we could compare them. So the first thing, let's calculate the electrical force, or the magnitude of electrical force. So the magnitude of the electrical force simply is equal to K, Q1, Q2, this is Q1, this is Q2, because we are dealing with electron and proton, so one of them is magnitude of charge of electron, the other one is magnitude of the charge of proton, and this is the distance between them. K value, this is our K. As I mentioned, sometimes I simply just say this approximate to 9, and because E is equal to 10 to the power minus 19, this is the difference between them. So it looks like the electrical force is a small force, 10 to the power something, 10 to the power minus 8. This is small. But let's go to the second part of the question. Try to find the gravitational force. Well, proton has a mass. Electron has a mass. Of course, electron mass is smaller, around 10,000 compared to proton, but they have a mass. So according to Newton's gravitational law, they actually attract each other by a force, Fg, right? And the force simply is equal to a constant, which has this value. Again, you should not memorize this. Multiplied by mass of the electron, mass of the proton, and r squared. Before you go through the solution, look at the similarity between Newton's gravitational equation and Coulomb's electrical force, or Coulomb's law. Very similar, right? But Coulomb came 100 years after Newton. Maybe he was motivated by gravitational force or gravitational law of Newton. Anyway, when you put the mass of these elementary particles, you get much smaller force. So Fg, gravitational force, also small, but this is actually very, very small. Because this is 10 to the power minus 47, is 10 to the power minus 8, which means electrical force divided by gravitational force is very, very, very large. It's 139 zeros in front. That's why when we solve problems in elementary particles, what we do, we simply ignore gravitational force. So we say Fe is way larger than Fg. So this is going to be ignored. That's why in all questions that we deal with elementary particles, we are going to ignore gravitational force between these elementary particles. Another example. Don't worry, the solution of this I have included in my next slide, but it's something I want to just do it together so you know how to solve these questions. Because when you look at the solution sometime in front of us, we might actually tend to not think too much about it. We just go over it. So it's important to do it by our own. So here what we have 3 point charges. So we have Q1, Q2, Q3. Located at the corner of a right triangle as shown in the figure. Q1, Q3, positive, and it's a 5 microcoulomb. So 5 10 to the multiplied by 10 to the power minus 6 coulomb. Q2 is negative 2 microcoulomb, and we have the value of A. We have the value of if this is A, so we know this angle is 90. We know this angle is 45. We know this angle is 45, so we know this angle is 45. We're going to need this in the solution. Now find the resultant force exerted on Q3. So we need to find the total force exerted on Q3. So the way I do that, I simply assume that I am Q3 because the question talk about Q3. So I assume I am Q3 and I'm a positive charge. So what's going to happen to me because of Q1? So let's focus on Q1. Well, it looks like Q1 is negative. So Q1 tried to push me toward Q2. So what happened to me, because I'm thinking about me, I am Q3. So there would be a force that tried to push me that direction. That force came from 2, so I'm going to just simply write it as F2. But because it's affecting on me, and my name is 3, so it's F23. Okay. Now let's focus on this charge. So what's going to happen to me, Q3, because Q1 is there? Well, Q3 is positive, so Q3 doesn't want me to be in that location. Q1 tried to push me this way. Because this force was generated or produced by Q1, so actually this force is F1, but because it's affecting on me, so it's F13. Okay. So simply F1, let's find their magnitudes. Just magnitude, I'm not putting arrow on it, so is equal to K. Let's put the rule Coulomb's law at the top, so we don't have to repeat it every time. Q1, Q2, R squared. If you do it between 2 and 3, this is going to be Q2, Q3. If you do it between 5 and 6, it's going to be 5 and 6. Okay, so this simply F23 is equal to approximate 9 to the power 9. Q2 is minus 2. Absolute value of minus 2 is just simply 2. So this is 2 10 to the power minus 6 multiplied by Q3. Q3 is 5 10 to the power minus 12. Distance between 2 and 3. Distance between 2 and 3, because we are doing between 2 and 3, is simply A. And A is 0.1. Don't forget to square it, equal to. So this is going to give me a number. I don't want to use calculator. So it's going to be equal to, let's say, question mark 1. Question mark 1. And this is Newton. What about F13? So let's repeat exactly the same calculation, equal to. Now, in order to know F13, we need to know the distance between Q1 and Q3. Well, the question did not give us this, but we know AA, and we know this simply R, so R is equal to A square plus A square, so R is equal to square root of 2A. That's how we got it, right? Okay, so it's going to be equal to 9, 10 to the power 9. It's between 1 and 3, so 2, 10 to the power, actually Q1 is 5, sorry. 5, 10 to the power minus 6. And 3 is 5. Minus 2. Q3. Yeah, actually they are the same, right? So 5, 10 to the power minus 6. My handwriting is not good. I think because of the tablet. Okay, so divide by root 2a, you square it, so it's going to be equal to a squared. And a is equal to 0.1. So this is going to give us another number, 2 Newton. We haven't done yet. We have not done yet. I want to just point out to this. These are two vectors. In order to add them, you need to use some method that you learned in the previous course, right? Component method. So when you deal with two vectors or 3 or 4, when you want to add them, you need to, one of the method is component method. So what you do, you try to find the component of these forces. So for example, F13 has two components. One goes to the right, one goes upward. The one that goes to the right, it's actually F13x. The one go upward is F13y. So let's find F13x. So F13x, it's simply F13 cosine of the angle, this angle, but this angle simply is 45. So we know this, simply in Newton. F13y is equal to F13 sine of the angle, which is 45. This is going to be another answer in Newton. Okay, so what's next? Well, next we need to find sum of all the forces, so sum of all the forces on the x-axis. Okay, so we have F23, it's already on the x-axis but on the negative side, so the sum of the forces simply is equal to F13 in magnitude minus F23. So we're going to get some number in Newton. Also, you say sum of the Fy, we don't have any y component downward or upward other than F13. So sum of the Fy simply is F13 sine of the 45, which is simply this number in Newton. So the rest is, we could write the total force, so the total force, F total, that affects on Q3, we could write in unit vector notation, is equal to I multiplied by sum of f of x plus j multiplied by sum of Fy. So this is done, but you could do one step further from here. You could actually find the magnitude of F total. So the magnitude of F total, see, you notice now, it looks like we are doing something in physics 1, right? Because it's just two vectors we are trying to find the resultant. So Ft is equal to, as a magnitude, is equal to sum of the Fx square plus sum of the Fy square. You could even find the direction of this. So let's say Ft makes an angle with the x-axis. Let's say the angle is called gamma. So gamma is equal to tangent inverse of sum of the Fy divided by sum of Fx. This is, we are done. Right? Now, if you go to the next slide, the full solution is there, but okay, now you know how to do it. So now I suggest you pause the video and try to answer the following question. Do exactly the same question, but this time answer, get the answer of the total force affecting on Q1. Of course, the answer will be different, right? But it's a good practice to do that. Okay. And only by practicing doing mistakes, you're going to learn. Only mistakes going to help you to learn. Okay? But if you see a slide like this, you go through it, you might tend to not think too much about the final solution or the steps or how the solution was done. Okay. So here the last step was actually not finished. Here you could simply, if you go back to my slide, these two steps were not done here, right? So you could do that. You could just finalize this. But that's simply a vector, right? So if you have this vector, everybody understands that how this vector look like. Well, actually, you could even draw it, right? So F3 means this is the total force affecting on Q3. It has a component on the negative, so it has something like this. This is negative, and this component is positive, so it's going to be like that. And looks like this is 7.9, this is 1, so maybe something even higher. So the magnitude of this will be something like this. Okay. Something like that. You could find the angle that you could find this angle, and you could maybe add it to pi over 2 or 90 to find the angle that the force, total force on Q3 makes with plus x-axis. Okay, let's keep going. Maybe another example. This time the solution is there because now we know how to do things. I assume you do practice. So question, or this example, we have 3-point charge again. 3-point charge lie along the x-axis as shown in this figure. The positive charge Q1 is 15 microcoulomb, is at x is equal to 2 meters, so it talks about this one. The positive charge Q2 is at the origin, so this is the origin. Origin is located here, at that point. And the net force acting on Q3 is, the positive charge Q2 is equal to 6 microcoulomb is at the origin, and the net force acting on Q3 is 0. So there is a negative charge. Q3 is located somewhere in between, not exactly in the middle, but the question tells us that the net force affecting on it is equal to 0. So the question asks, what's the x coordinate of x3? Simply, at what position we should put Q3 in order to the total force affecting on it is equal to 0. Notice that I said the total force, because net force means the total force. So before we go deep into the solution, let's think about it. Because the question is about Q3, so let's assume I am Q3. So I am a negative charge and I am somewhere here. So what's going to happen to me because of this positive charge? Well, this positive charge wants me to go toward it, so this is the force. Control Z. No, I am trying to pointer, eraser. Okay. Now again, pointer, pen. Okay. So this is the force, and it's F13. What about Q2? Well, Q2 also tries to push me or pull me toward its direction to the negative side. So this is the F13. For a second, if Q3 was positive, well, if Q3 was positive, Q1 will push it away from it, and Q2 will also push it away from it. So again, you will have two opposite direction forces. So what we aim here, we know that this force in direction opposite to this, but their magnitude are the same. Their magnitude is the same. So we could say the magnitude of the F23 is equal to the magnitude of F13. How do we know that? Because the question says the net force is equal to 0. So their magnitude at least has to be equal to each other. Now, how you solve this kind of thing? Of course, this is something in high school. You could say you have AB is equal to CD. So what do? You multiply this by this, and you equalize it to multiplication of this by this. So you simply say AD is equal to CB. Okay? I'm sure everybody knows that. Okay, so that's what we do in this case, and we're going to get into this. So we have Q2, Q1, but we know their values. We know their values. So in the next step, we square this because we want to get rid of of this square. We want to get rid of this square. So if you square this, you're going to have the square of the first bracket will go away, and Q2, actually, sorry, you don't square it, you take a square root. You take a square root of it, so the square of this will go away, Q2 will be square root, x squared will be x, and Q1, and we have a plus minus, right? Because every time you take a square root of a value, you have two possibilities. You take a positive or negative. That's why you have this. And of course, we are looking for x. So what do? You move this to the right side. So it's going to be here. It's going to come here. And then you switch the direction. And this is our x. Now, our x will give us actually two values. Give us two values. One for negative, one for positive. The accepted value is 0.775. Means if you put Q3 at that location that has x is equal to 0.77 meters, it will not move. Looks like a person there. Think about like a person there and two guys pulling it. One to the right, one to the left with the same force. So that person will stay in that location. Okay. Another example that includes something from Physics 1 previous course and something from this course. Just to, demonstrate that we are dealing with vectors. So it doesn't matter if these vectors are tension or electric force or gravitational force. So this is a nice question. I'm not going to go through it, everything, but at least I'm going to give you some idea at the beginning, but because I want you to go through this solution from the textbook. I really want you to read and use the textbook. So, but let me explain some of the things here. So we have two identical small charged spheres, each having a mass of this value, hang in equilibrium as shown in this figure. So it's shown here. So it's hang from here. Okay. The length L of each string is given. So L is given, this L is given. And the angle is 5 degrees. Find the magnitude of the charge on each sphere. Of course, the first question is, if these two spheres were not charged, they will not repel each other, right? It will be something like this. Just something here and something next to it, right? But because they are charged and they have the same signs, plus and plus, so they don't like each other, right? So they repel each other. That's why they are going away from each other. That's the whole point. So the question says, find the magnitude of the charge on each sphere. So what we do, we need to have a free body diagram, at least for one of them. Free body diagram for one of them. You could write the free body diagram for the left charge, or you could write down the free body diagram of the right one. So the free body diagram for the left, simply two forces affecting one, actually three forces. So you have a typical mg, gravitational force. You have a tension because you have a string. And you have the electrical force because the question says they are charged. This electrical force is Fa. Okay, now we don't care. It's not important if this is tension, this electrical force, this mg. The importance, there are three vectors, so we need to be able to deal with them. Okay. And because it's equilibrium, means the total force affecting on Q is equal to 0. But remember, this is a two-dimensional problem. So you need to demonstrate and know that summation of Fx is equal to 0, summation of Fy is equal to 0. Okay. Well, T has two components. One goes to the right, one goes upward. This angle theta, so this angle theta. Okay. So this is T sine theta, this is T cosine theta. So very simple. this force has to be equal to that force. And this force has to be equal to this force. That's it. That's a solution, right? But I want you to go through it and solve it completely. I'm gonna maybe pause the video here, then I'm gonna start later.